Yeah, so I'm John, work in Google in Accra and also Makerere University, split between the two. Data Science Africa is usually one of the highlights of the year, and this is no exception. I'm loving Ethiopia. This is great. Usually, always. Yeah, in the last 6 years, have I had any other highlights? I don't know. Yeah. One of the things which is really nice in Data Science Africa is we're starting to have the people who were students before being the instructors in these sessions, which is great. It's also really good for learning, because I think when you have to teach, then you really actually learn the stuff quite well. So one thing we haven't done is with this spatial analysis course, have one of the former students do the teaching. So if anyone is interested in this, then come and find me later, and we could have someone take this on to maybe have a practice run of teaching at one of the, maybe next Data Science Africa or something like that. Okay, so spatial analysis. We had time on today. We've got space now. So I mean, what else would you possibly need? This is everything. Spatial analysis is much more interesting than it used to be, because there is more machinery which collects interesting data. We're going to go through two examples today with kind of representative of the different types of data that you might get. So one is spatial data from GPS, where it's like point locations, and maybe from certain points you're trying to figure out like what's going on elsewhere. And another type of interesting spatial data is coming from satellites and remote sensing. And that's a bit different. There you observe everything, and maybe the challenges are trying to infer from what you see, like other things of interest, or maybe predicting in the future. So we're going to do two examples. And the first one will be a crop disease mapping example, and the second one will be trying to predict deforestation in East Africa. So let's start off with the kind of game. This is back to the gambling theme. The casinos keep coming up. I want to pose a kind of gambling game to you here and see what you think. In the notebook, I've generated a two-dimensional probability distribution. Okay, so there's some kind of underlying probability distribution. Like, I'm going to draw samples from that distribution one by one, and some areas in here are like more likely than others. And I want you to imagine this game. Imagine I've given you like 100 coins, and there's 100 squares on here. And you can place the coins wherever you like on any square. You can place all 100 coins on this square, or you could put one coin on every square, or half and half, whatever you like. And we're going to draw samples. We're going to draw a sample from this distribution, and let's say wherever the sample falls, however many coins you have on that square, you get to keep those coins. I'm a bit low on coins, so we have to just do this in our imaginations for now. Okay, so before we've seen anything, you don't know anything about anything. Like, any thoughts on what you would do? Just now, like if you were trying to maximize your reward. What strategy? Any risk takers who would like put everything on one, or what do you think? Please.
Do you mind explaining the goal again?
Thanks. Yeah, great. So you've got 100 coins. You can distribute them anywhere you like on this grid. We're going to take a random sample from some distribution that you don't know, and so the sample might be here, or it might be here, could be any of these. It's some distribution you don't know, but it's going to be one of these. And wherever you've allocated the coins, however many coins you have on that particular place, wherever the sample falls, those are the coins you get to keep. So what I'm asking is, how do you distribute the coins? Like, are you going to kind of trade off, like have some places where you put more coins, or are you going to put them equally, or what do people? Does that question make sense? First of all, is anyone confused? Yeah. Okay, Mike.
Yeah, that's sort of a question. So it's like getting 2 coins kind of twice as good as getting 1 coin.
Great question. Yeah. So
that affects the decision on
That's a very good point. Yeah, like maybe it's non-linear. Like perhaps you don't really care about one coin. Like John's made up 1 coins. I mean, who cares about one? I either want to get all 100 coins, or I'm not interested. And then if you felt that way, then maybe your strategy would be a bit different, right? Any other thoughts on strategies here? We haven't seen a single sample, so I'm not surprised there aren't so many suggestions right now.
Well, so the question is, how do you want to distribute the coins, right?
Yeah.
Yeah, and you're asking how would I do it?
How would you do it? Exactly, yeah. So that when a sample comes along, you're choosing where to put the coins. From this distribution, we're going to randomly sample, and wherever the sample falls, you keep those coins. Do them uniformly. Makes a lot of sense, yeah. If all of the coins are equally valuable to you and all of that, then sure, one coin per square. That makes a lot of sense, yeah.
If it isn't linear, if your like reward is linear, so the number of coins you get, then it doesn't matter, right? They're all equally, because once you time your probability by the reward, it ends up being the same for all possible choices, right?
Yeah, if we were to repeat this many times, and we're in exactly this situation, and we could go through infinite. If you had infinite number of coins to kind of keep doing this to keep playing, then maybe it doesn't matter. Maybe you could just put them all there and keep playing the game, and eventually you'll. But uniform kind of makes sense. So let's go straight to another one. Let's draw our first sample.
That's weird. That's where I was going to put it.
Man, 100 coins. Geez, right there you go. All right, so great. If you'd mentally allocated all your 100 coins there or whatever, then congratulations, you win. Okay, so we've got one sample. And I guess what you'll observe is that this kind of gets easier and easier the more samples you get. Like we get more information about what's happening. Okay, so we've seen one sample. So like maybe this distribution, maybe every single time, I mean, we choose this square. Perhaps the next sample we're going to get is also going to be that square, and it's going to be that square again, and that square again. Or maybe it's completely random and they're all over the place. And we're going to try to decide. So I think we had one kind of serious strategy for the last time, which is like uniform. Does anyone want to evolve on that strategy now that we've seen one sample? Or are we still cool with like uniform? Are we still going to put 1 coin on every single one of these squares? Or yeah.
I think if you have one example that you show, you can some role model, create a model that generates this data, and you can optimize your strategy using this one.
You could create a model and try to optimize your strategy, yeah. So maybe a way of saying that is you're trying to guess which areas specifically are more likely than others. Your model is maybe trying to work out what that probability distribution is, something like that, yeah. Yeah.
I think I would stack my 100 coins around that 1 coin.
Uh-huh.
Get them stacked around there.
That seems like a cool strategy. Okay, so we'll take them away from like these areas, and there's going to be a kind of pile of coins here.
What I don't understand is, are you trying to make whoever opens up that box richer, or you're just trying to make him get less money?
So it's not adversarial. Yeah, the probability distribution is like independent each time. So the only where the strategy comes in is like for you as the player to try and maximize your reward. Like from the kind of this end, from the choosing the samples, this is, I mean, like we it's completely neutral. It's just like the samples come according to a distribution. Yeah, it doesn't. Like from this end, it's not reacting to how people allocate their coins or anything. It's just like drawing samples independently, IID from each time. Yeah, yeah, great question. Yeah. Yeah.
I'm going to go with Ernest. Because I reckon it would be pretty weird if you to then decide to go completely random. Like, everyone would be like, that's a weird decision. But then if it was all just on 1 point, that would be a bit weird as well. So I reckon you're going to end up with a nice looking picture at the end. So that's my fire.
Yeah, right, exactly. So maybe that's one way of reasoning it through. I mean, it'd be kind of disappointing if I went to all this trouble and it was just completely random in every location. I mean, maybe there's going to be something non-random or like non-uniform. Yeah.
Yeah. So I guess I don't know if it's fully understood, but I guess the idea is if so I want to put my 100 coins somewhere, and if your model, whatever you have under there, selects the spot where I put my coin, I get those coins, so it's maximum, right? That's the idea?
Yeah. Mm-hmm.
Yeah, I don't know if it's confusing or not.
Yeah, I hope I haven't confused people. Yeah. But yeah, exactly. Okay, so yeah, so we've had one sample here, so a kind of extreme strategy. You know, if you're like a extreme gambler, you could say, well, we've had one sample here, so the kind of extreme of Ernest's suggestion of like put a pile here would be to just put that pile all on this one thing. We could say I've seen a sample there, so I know at least this one sometimes comes up. Let's just put all 100 coins on there, and maybe it will come up again, and I'll get to keep all those 100 coins. Or depending on how much you like risk, or how risk averse you are, you might spread that pile out, right? Like, so you know, I guess you're saying not all on that one, but maybe kind of sort of around there. That might be a strategy, which totally makes sense. This is still pretty difficult. I mean, you've only seen one sample here, so that's kind of cool coming up with suggestions already, even just based on one sample. But I think we're kind of dropping the completely uniform thing now that we've just seen one. Well, or are we? I don't know. I mean, yeah. Don't let me put words in your... Not yet, okay.
That should never make sense, right? If you've got one sample, then that should never change that.
This is an interesting point. I mean, uniform, like you know that the sample's going to come up somewhere, so... I mean, maybe like, why would that... Yeah, exactly. I mean, why would you change it? Okay, is it time for another sample? Let's two samples. Okay, well, let's go for another. Let's have three bonanza. You've now got three samples to.
Give us a phone.
Since it's Shira asking, I'm going to give you a fourth. Yeah. Anyone else? I don't know. I have to think. Okay, so the more this comes on, the more information you have to deal with, and perhaps you can make more sophisticated judgments. Like, I don't know, any observations like about people's what's people's gambling strategy now? Now that you've seen 4 samples, yeah. Comment here.
You put your coins on one column, then skip the next one, then another.
Ah, interesting idea. Yeah, sure. Equally valid as anything else. I mean, you don't know. I haven't said anything about like whether it's yeah. I mean, there's no reason to think that. I mean, maybe it spells out a smiley face, or or it's in columns, or yeah, exactly. Everything is on the table at the moment. Yeah. Other ideas? Yeah. Matembusa?
I'll place them halfway. Very good. I'll place uniformly, but on the halfway point. So the first 5 columns to my left.
Yeah. Interesting. Okay, so like, yeah, sort of seems like they're on this side. Also seems completely reasonable. Yeah. One there. Yeah.
Okay, so it seems like they're able to fall into quadrants, and the third quadrant seems to have more. So it's more quadrants that are.
Okay. 1, 2, third quadrant, or like this quadrant here. Yeah. Right. Yeah.
Below the diagonal.
Sorry. Oh, the below corner. Yeah.
Below the diagonal.
Below the diagonal. Yeah. Sure. These are all completely reasonable answers. There's no right answer at this stage, right? Like, we can hypothesize. What I would love to do if I thought about this and we had the means would be if everyone could do their allocation. If we averaged those allocations, I bet you'd get a pretty interesting. I bet we'd get something kind of quite cool, like some average of all of these things. Okay, well let's kind of give a bunch more, and like, still, even if we get up to like 50 samples, we can sort of see that something's happening. It's probably not uniform. This stuff towards down here seems interesting. Let's have a load of samples. Let's have like 500 samples. Yeah, okay. So like when we start getting, the more and more you have, then the more information you have to go on. And you can start seeing that, yeah, maybe there's some underlying like smooth distribution. And yeah, some regions are more likely than others. Yeah, I think probably anyone who was hanging on to the uniform distribution at this stage, like, would probably be thinking, yeah, maybe, like, is this area which has had 0 samples really as likely as this one which has had 17 samples?
They're risk neutral.
If you're risk neutral, if you're really risk averse. True. This is like a personality test. If you're really like, I'm just going to insure everything, I just want to have my coins equally everywhere, then that's a good sign of personality. And if someone's like 19 samples there, 100 coins, bam, yeah. So it depends a little bit on some extra factors. Here's the true distribution, the underlying distribution. So I generated this with some code that's up in the notebook. So if you want to try a different random seed and do this again, you can play around with that. So this is, if you had lots and lots and lots of samples, then you'd eventually get this. And hopefully it's clear to people that assuming, okay, maybe with some assumptions, what you're trying to do is kind of, you might think of allocating your coins according to this probability distribution. At the very least, you probably want to know what this distribution is to make your decision. The more you know about this distribution, then the better choice you can make. And probably, I'm guessing what most people would do, if they knew straight up that this was the underlying distribution, like these are the most likely places, this area is very unlikely, probably most people would want to put more coins on the likely area and fewer coins on the unlikely areas, right? And in the limit, you maximize your profits in this game, this weird game where I just only give out coins and never receive anything. You would maximize that by knowing what this distribution is. So the problem here is that we're trying to take some of these samples, and we might have just a few numbers, some like this, and we're trying to guess what this is. This might seem like a kind of a game or a toy example. There's lots of real-world situations that are quite similar to this. So imagine these were something like traffic accidents or something, or like cases of some infectious disease. Okay, infectious diseases may be a bit complicated because of the time. Maybe non-communicable diseases are better. And from some samples, you're trying to work out what's the underlying risk or the underlying probability. And the better you know that underlying probability, the better you can make decisions about whatever that is. In the case of traffic accidents, maybe you understand where are the hotspots of collisions, and then the city planners can do something about it, or you can know not to go on that road. So let's think about how to do this with as few samples as possible. If you've got lots of samples, let's take like, 10,000 samples. Okay, so if you take 9,524 samples, then you basically just get the distribution back. So in a world of infinitely being able to observe anything you're interested in, then you can relax, right? I mean, this is basically the probability distribution there. So if it was, if that was true and you had lots and lots of data, the more data that you have, the less hard you have to work, basically. But then the world's not like that. Usually you have limitations and you want to do the most with the data you have, especially if it's traffic collisions. I mean, you don't want to wait for 10,000 traffic accidents before you start to draw some conclusions. I mean, that would be kind of late in the day. Maybe after 20 accidents, you might start to already try to make some recommendations if this was your job. So I've got some suggestions about what you could do with a few samples, but let's hear some of your thoughts. Like, if you've got just a few, say you've got 50 observations, and you're trying to do the best job you can at taking this and working out what that true probability distribution was. Maybe these are the traffic accidents, and you're trying to work out like where the underlying risk is. So one thing I'll point out here is that you can't really go much further than the data without making some assumptions. This is fundamental to all data science, really, unless you just want to reproduce the data. If you want to do anything more interesting, then you've got to decide a model of some sort. I mean, a model is encoding some of your assumptions about what's going on. So one thing here, you could assume, for this example, that there's some spatial smoothness. So the underlying value of the probability distribution in the one square is going to be similar to its neighbor. Let's imagine like we use that. So this is true for lots of stuff. True for things like weather. It's unlikely that it's raining really heavily here, and right next to it it's nice sunshine. Same with disease maps. Unless you really know that there's something else going on, maybe there's some risk factor in one place or another, unless you have information like that, you assume this kind of smoothness, that like nearby places have nearby stuff going on. So if you know that, is there any way you can take these observations and go to maybe a slightly more sophisticated map of the probability distribution than just using the sample probabilities? Yeah, Billy. Smooth them. Yeah, smooth them with that suggestion. Yeah. Totally. Yeah, it's no trick question. Yeah, just kind of smush them around a bit. Like, this value here is 0, and the one next to it is 4. So do we really think there's like 0 probability chance of anything coming up here? I mean, we've seen a bunch of stuff in this area, and we know that, I've told you that this assumption holds true in this case, that neighboring cells are close to each other in probability distribution terms. So this one probably isn't 0. I mean, probably we want to take some of this probability mass from here, because we've seen some samples, and kind of, like smudge them around a bit. I'll speed up a bit here because lunch is coming, and we don't want to. People's attention might suddenly start decreasing. Let's think about how to smooth stuff. We're going to go back to one sample, and we're going to think, like, from a single sample, what do we do? Remember that question I was asking? We saw our first one, and like Ernest was saying, well, could we kind of make a pile around that one sample? So here's a pile. Like, I don't have the numbers here. They wouldn't make much sense anyway because it's quite small quantities. But we've got our pile around here. We're saying we've got one sample. We know that smoothness is true, so let's kind of put a bit of probability mass like around that area. And then there's this question of like, well, how big or small should that mass be? So we could have like a sort of big pile, or a really tight pile, which is just only that square. So we've got some decision to make there, but I don't know. Let's choose that. And then, as we have more samples, then we can keep smoothing out the distribution around that. We'd normalize it each time, so everything adds up to 1. So it's a nice probability distribution. But basically, each sample we allocate some more around there. So that's 3, and then interesting things start happening when you've got like, 2 in one location, and now we've added an extra blob on here and normalized again. And this estimated probability distribution is starting to take shape, right? Like this is gradually looking a bit more like the true distribution. And we haven't quite decided how much to smooth, how to do this. If we make these sort of wider blobs, then if we make them really wide, then you have a more smooth distribution. And if you make them really tight, then you're back to just the samples. But maybe somewhere in between is the right answer. And as you add on these samples, so with 12 samples and an assumption of smoothness, you're not doing too badly at recovering the true distribution. Like even though this doesn't look too promising, but simply with the smoothness distribution, that estimated what's the probability of any particular square being chosen is not super different from the true distribution. Does this make sense? Any questions? So there's something we haven't done yet, and that's to work out how wide or how smooth is smooth. Do we make big? Do we do a lot of smoothing and it's really smoothed out, or we do a little bit of smoothing and it's not so smoothed out? This is a problem of parameter estimation. So we have basically different possible settings that we could use here for our estimator, and we've got to choose which one is the best with some amount of data. So in general, with some data, when we're trying to choose between different models or different parameter settings, like how do we do that in general with machine learning? Got some data, you're trying to predict something, you don't know whether to use this model or that model. Cross-validation, yeah. So we can do the same thing here. Cross-validation, or what I'll do simply here is just have a training and test split, can work on loads of stuff beyond classifiers and that kind of thing. We could say, give us some samples. Say you've got 10 samples, let's use some of them to kind of train a model to do smoothing at different smoothnesses, in this case, and then we'll see how likely the other ones that we've left out are according to that. I'll leave the details for you to go through because we're running a bit late, and I'll show you the examples, and then maybe you'll get some intuition about this. So I'm starting off here with 2 samples, and I'm going to do a training and test split. So meaning our training set size is 1 sample, and our test set size is 1 sample. Big data. So the smallest possible set you could have. Is that a question or a stretch? It's time for lunch. Okay, so like if this is our training sample and this is our test sample, then we try different smoothnesses and we choose the one which gives us the highest. See if it does something interesting. As we get more samples, we're starting to kind of choose a smoothness. We've used some of these samples to train and try out different smoothnesses. We're using the remaining samples to select which is the smoothness that gives the best predictions of those remaining ones that we left out. And I'm drawing this thing here, which is the log likelihood curve. So I've taken the probability as calculated from the smoothing. I've taken the logs of that because logs of probabilities are much nicer to deal with. It's a negative number, and the higher it is or closer to 0, that's a better model. And so what I'm showing in the star is like the smoothing value which gives you the optimal. And so this is a way of automatically choosing the best smoothing constant. Question? Oh, the axes of the graph. Yeah, sorry, this is tiny. Yeah. hope some people are at least able to have obtained these notebook files so they can see. Sigma is the parameter which decides the smoothness of these, like how much smoothing we're going to do. And this is log likelihood, which is basically a score for how expected or unexpected those left out samples were. So I've used 20% of the, like, for test data or validation data, and like how surprised are we by those remaining ones according to the model we've learned? Yeah. So the higher up, then the less surprising, or the kind of better the model's fitting. So we can do this automatically. So this is kind of one way we could approach that kind of like gambling game earlier on. So you get like a bunch of samples, and the more you have, no, it's still choosing quite wide. That's not really the right answer. Yeah. Okay. So sometimes it seems like sometimes it chooses like big smoothing factors, and other times not. All right. Let's put this into practice. So we're going to deal with some real data here. One of the other cool things about Data Science Africa is each year the examples become a bit more practical and a bit more African because our projects evolve and we actually get stuff from the field. You know, maybe next year we'll be doing this with the IoT devices. You know, they'll be running in greenhouses around the place, and we can use that as the example. We're going to use some data from the project of these guys you see, Ernest, Solomon, Mutembeza, and they've been putting a great deal of work into ad hoc survey with farmers around Uganda sending in photos of cassava plants. Then they get like diagnosed, and we're able to try to do various types of machine learning on it. So these are longitudes and latitudes of data submitted by, I think, mostly farmers, right, from across the country. And I've just chosen, they're interested in a range of diseases. I've chosen one arbitrarily, which is cassava brown streak disease. So we've got longitude, latitude, and whether that plant had brown streak disease or not. And so we've got lots of data here. So this is a kind of simple table here. Each one of these is like phenomenally difficult. I mean, this database here is like a few thousand examples, which is like blood, sweat, and tears. I mean, all this coordination, getting smartphones out to farmers and training them and having the data systems and all that. Like, you can't imagine what's gone on behind every single row of this data set. But let's think, okay, what if we're getting this data, so we might want to map it. And if we just map the examples here, then we've got like yellow examples are the ones where there was cassava brown streak disease. Blue are the ones where there's no cassava brown streak disease. And maybe you can kind of see some example, but it's a bit like the previous toy thing where like the samples aren't really enough on their own. I mean, you can't really look at this and really quantify, is this area more risky than that area? Or the samples are only for some places, like other places we don't really have much. So that's another factor here. Maybe we're better able to make predictions some places than others. But the way we can approach this type of problem is pretty similar. There's some differences. So here we've got, our observations are a bit different in that before we only had like one type of observation, like a sample can be drawn. Now we've got like negatives and positives. We've got like zero disease or like disease. And so what we're trying to predict here, our underlying distribution, is a bit different, right? But many of the same concepts from what we looked at before also apply here. I'm going to go straight to the results of what happens when we use those type of concepts that we discussed in a slightly fancier model called a Gaussian process regression, which is a bit like what we did before, but with some extra concepts. One of those concepts being given the data we have, we can be more confident about some places than other places. So we've got observations of some areas, not observations of other areas. So maybe here we don't really know what's happening. And if we try to make a prediction, maybe it won't be a very good prediction. So perhaps it's best to just say, like, don't really know. Whereas here, you know, we've got lots of activity, so we're maybe more confident about that. But otherwise, we use the spatial smoothing assumption. We can either set how smooth we think smoothness should be. In this case, there's actually some underlying biology, so we can actually have a reasonable guess at knowing how smooth. You know, what's the length scale at which things affect each other. But we can also optimize this, you know, according to the statistics from the data. And long story short, you run some code which looks like this. pretty simple code. The hard work's kind of done for you. And then we can plot it like this. This is what we get when we, I've just chosen some length scale here and I'm plotting it. Plotting spatial results with uncertainties, a trick here I got from Mike actually, which is like you get the uncertainty at each point, so you can you can plot them with some marker and scale the marker according to how uncertain you are. So lots of observations around here, big markers. Down here, basically no observations, so the markers just shrink to nothing, and we don't really try and predict anything. So this is something like probability of cassava brown streak disease, according to our data, which we weren't really collecting it as a survey particularly, more to like collect data to train a classifier, so they may have been hunting out the diseased leaves and things like that. It might not exactly, if you live here, don't uproot all your cassava plants just based on this. There's maybe something about study design and that sort of stuff. But that's how that data would be used to get some kind of map like this. Does that make sense? Any questions?
Sorry, I'm really intrigued by the length scale. Is that like, did you decide to end up fixing it in biology, or did you fix it in
I fixed it here, length scale 0.5, so about 50 kilometers. We did once try to speak to people. We spoke to Titus in Makerere, and we're asking like, if you surveyed in one place, like how far away would you want to move? If you really knew what was going on here, how far would you need to travel? And then kind of got an idea of the length scale from that, how far the whiteflies travel and stuff like that. So kind of based on that, we have a sort of bit of an idea. But you can optimize, which is basically doing what we did before of trying the different ones and seeing which fits the data best. Yeah. Other questions? Okay, how are we doing for time? I think it's totally lunchtime. It's totally lunchtime. All right, so I'm just going to, I'm not really going to go through this notebook. There's another notebook with another cool example which you can look through later. I'll get off the stage here so we can go and have lunch and move on with the program. But this example that you'll see is about predicting deforestation. And this is a bit of a different type of example where you observe everything from satellite, and the prediction problem now is in time. And what we're doing in this, so this is the data of forest cover in East Africa. So we've got Uganda, Kenya, and Tanzania in the year 2000. And in the example here, you'll see there's data for each of the years up to 2017 or something like that. And we're going to try to predict the deforestation each year. Occasionally there's reforestation, but it's more or less a deforestation prediction problem. And we're going to do that based on some factors. So you'll notice one of the things about the problem I just showed you was we didn't look at any covariates, which maybe are useful. Like in the cassava disease case, I mean, there's some places where there's not really much cassava. Some areas of water bodies where you can't farm anything. I mean, it's a lake. Or you might know that certain interventions have been made, or they're growing different strains of crop. So there could be various extra factors that we might want to incorporate here, and that's actually very simple to do in this type of analysis. So that's the example here. So what you'll see is that there's some other types of data, like where are there roads, for example, is pretty useful. Like point locations of roads taken from OpenStreetMap across East Africa. And this idea of smoothing comes in. Smoothing comes in quite a lot in spatial stuff. Unless you really have reason to assume otherwise, then usually stuff near to each other is kind of similar. So we can take points of roads which are like 1 or 0, road or not road. We can do the same kind of smoothing, blurring operation here. You'll see how to do that in the notebook. And you get this measure of like how roady, how concentrated are roads in that area. And then we can already sort of make out these kind of urban centers where there's lots of roads, and nature reserves and water bodies where there's not many roads. So that's one covariate that we can use for our predictions. And then we can make a classifier which is trained by taking for each year, like which are the covariates previously and then which deforestation happened. So the training, the inputs that we might have, the features are like, where did deforestation happen last year? Where are the roads? Where are like environmental factors? You could bring in economic factors. We also include here whether it's a protected area or not. You know, that seems like another useful covariate here. And with all of those, we can train a classifier. And in that type of thing, you don't really have to be, it doesn't matter too much about this being spatial. The x and y, the longitude and latitude, are just two features which go into your classifier in that case. So you've got longitude, latitude, is it a protected area? How much deforestation was there in that location last year? And so on. Train a classifier, which we do here, and I'm using a gradient boosting classifier. It's quite a good general purpose thing. These are all quite different types of inputs, so that tends to work pretty well. And you can just measure this with ROC and view a deforestation forecast. So this was the forecast for 2016, which is now in the past, so I guess we can check whether this was right or not. And so, yeah, bad news, guys, Ugandans. Check this out, yeah, like Western Uganda's is looking at risk, and also the kind of eastern seaboard of Tanzania. So you can run through, you can get this deforestation. The links to the data are there, so if you want to take this further and see what's the, how good was this prediction, and what's the prediction for next year, then go for it. Yeah, so I think we'll basically leave that there. Any quick questions? Find me at lunch if you want to discuss further. And if you are interested in this and want to actually try presenting it another time, then also come and find me. Okay, Billy?
Is it possible to sum up, because so development happens, urbanization, and part of that contributes to deforestation, but some of it, because you can look at certain images in new houses, but not every new house is that happening.
Yeah, covariate design. Yeah, so the only thing we've got representing urbanization here is this road network, and then the kind of smoothed road network, which is kind of a proxy for like human population or like activity or economic activity or something like that. So yeah, you could imagine more sophisticated versions of this having that type of thing. Like maybe from satellite data, you can know where buildings are, where new buildings being built, what type of buildings are they, what's the delta from last year, and maybe that would be a better covariate or an additional covariate. And probably the more of those you bring in and add as features into the classifier, then the better the prediction gets, I imagine, yeah. Okay, we'll break there. Thanks for your attention.